CCast or something else, but just in the last homework, we were drawing models and not. Oh, sorry, I didn't show my image. It's not. I'm not so. It's not my main goal to be recorded and so I use. But now it's probably easier to communicate. Thank you, Kia, for mentioning it. So, especially if you practice Avogadro on your personal laptop, after making each model, please consider to upload it to your directory on the photon. And when you're doing presentations, you may also remind. I'll bring back your choices, but there will be only one person who will explain basics of Linux and transfer of files, but others may revisit this subject and tell, after I create my model with Avogadro, I do this and that command to transfer the file into Photon. Okay? Another comment along these lines. Again, if you are working with Gauss View, your life is slightly easier because Gauss View create files literally prepared to run Gaussian. If you're working in Avogadro, you are creating PDB or some other format. So I'll plan to show it tomorrow, but we all need to, especially those who work directly with Avogadro, upon transferring the file, one needs to modify it with Babel or manually and add some specific keywords that belongs to Gaussian to enable future calculation. So it's not a big deal. It's a matter of 30 seconds, but just do not skip, do not forget about it. So in this sense, Gauss View is a little bigger. I still didn't found why Gauss View was not working on Sarah laptop. I think it is some security reasons. There is some in your settings of your laptop, you selected it to be very suspicious and cautious and prevent any remote connections. Once I did fix it for my computer, and if we go to the security settings and compare them one by one, probably we will fix it on your computer. I do not promise that we will do it quickly and in time, but it seems possible. Okay. Here is an assistant to our class.
Oh, he's so cute.
I think, and I think he's tired of relaxing and he needs to
Oh
go.
my god, what is his name? He's or her?
Huh?
What's his name?
Name Mickey, like Mickey Mouse.
Mickey Mouse.
Yeah, not mouse, just Mickey.
Mickey cat.
Maybe he will return in the middle of the class to help us. I see something on the chat. Oh, okay. I think it is comment more about the assistant rather than about the class. Oh, I think he has returned. Okay. So, and the remaining comments about the presentations. Boston, please remind me tomorrow during the class. Maybe I should do it at the very beginning because it's like very quick to show databases. Maybe you already found them, but I'll better make a little demonstration. And it is slightly disconnected from the rest of our activities. So maybe I'll start from it and then go to the main story.
All right, sounds good.
Yep. Okay. And I did send you some brief email about projects. We may continue discussion just to agree on little details. So I need to admit I didn't watch on my slides for today's lecture. So it will be first time since last year we will open them together. But here are the general directions of the course, what we are looking for to do. So last time when we finished, I did introduce an analog of Ehrenfest theorem, a transition from the quantum limit to classical limit that brings us from, and do not worry, I'll show equations once again. It's better to chat first. So going from time-dependent Schrödinger equation for nucleus back to Newton's equation. So maybe I'll chat and show some slides more about these transitions, but then after we are done with this transition, after we are done with the description of the potential energy surface, and I do believe there are some slides from you on the definition of the potential energy surface. If you didn't complete, you can send a little later. But after we get to Newton equation, after we introduce and connect it to potential energy surfaces, we will arrive to understanding of the main problem, I wouldn't say main, first problem in any computation, so-called geometry optimization. Basically, if we do have equation of motion for each ion in the model, we need to find at which interatomic distances they will stabilize. And we need to get a basic idea about the algorithm, how the optimization is happening, how the computer browses through the potential energy surface and finds the minimum. If we will be done with this algorithm, then we will be done with the chapter 1 of the class. So I will see, based on the slides, is it possible to complete today? If no, maybe we will complete it next Tuesday, and then we will start next chapter. Okay. And in a few seconds, or maybe a little longer than a few seconds, but very soon, I'll start sharing the slides. Okay. Okay. It looks like I'm going to entertain or bother you with more equations. So we will do algorithm on the next Tuesday, and now I will provide some additional support for this transition. So my own assessment that it is secondary to the main goals of the class, to the practical things, and you can just lean back and relax. I'll attract your attention if there will be something important, but the things that I'm going to show will be, in some sense, secondary. At the end of today's meeting, we should agree on the content of this yellowish box. We should have set of equations for electronic part and nuclear part. At the end of today's meeting, electronic part will be still quantum, and nuclear part will be completely or almost classical. So basically, we did it in the last meeting, and I just want to give a little bit more details so that you feel comfortable. It could be a very legitimate question from your side. Why do I need this equation? If my goal are practical engineering and material, why do I need these transitions if they're not used towards practical thinking? The answer. I hope you all do keep ambitions for writing degrees and papers as first authors. Like you all have your advisors, but typically graduate student writes a paper as a first author, meaning being responsible for almost every word in the paper. And then when the paper is submitted, it is revised by reviewers who try to find weak places, weak spots in your papers. One of the aspects, if your paper will ever contain computation, will be methodology and list of approximation. So in order that you look like a fellow computational chemist to a reviewer, we all should mention approximations in a reasonable way. So what I'm showing you right now will be not used for your practical project, but if you remember like 5–10% of what we discussed right now and mention it in a right place of your method section or list of approximations, you will impress the reviewer and your paper will go through. Make sense? Okay. So, and we suffer a little of torture with equations for this big goal. If you do not like them, you can just lean back and I'll summarize most important things. So then at the beginning we started with molecular Schrödinger equation, and then with Born-Oppenheimer approximation we chopped it onto electronic and nuclear part, both quantum. Electronic quantum part, nuclear quantum part. Nuclear quantum part gives us this chi wave function, nuclear wave function. And if we perform this operation of finding expectation value, which is standard in quantum theory, one is obtaining the expectation value of position. So wave function, observable wave function, integral in the variable over which we integrate, differential. In this traditional thing is often recorded in Dirac notation, where integration is replaced by this little angular brackets. But if we assume that such procedure is available, then for each configuration of the molecule, where instead of spatial uncertain distributions of positions of ions, we can go back to literal positions, expected value, what are more probable places for each ion where its coordinate will be. To look smart, we are telling it is not just a coordinate, it is expectation value of the nuclear wave function. But in fact, it is the same as the classical coordination for Newtonian equation. If we do have this expectation values of the positions for each ion, I can put here the subscript I for each ion. then one can find a force that will correspond, that will act on given ion, will act as a reason to change this expectation value of position of ions. And this force will be gradient of the nuclear potential, which was always in the classical mechanics, right? Gradient of potential is the force. And additional term, which is gradient of electronic Hamiltonian, or through some transformations, it will be will go to the force, to the quantum contribution to the classical force. And after we go through these two panels, we will arrive to equation that looks very much like Newton equation of motion for the ion. Second derivative of position equals force divided by mass, which is like acceleration equals force divided by mass, right? Or some people like different form. Instead, some people hate second derivatives and they do separately first derivative for position, first derivative for momentum. But these two forms of Hamiltonian and Newtonian equation, classical equation of motion, are equivalent. So if we will arrive to this slide again at the end, I think it will be sufficient. And next time we meet in a week, so on Friday there will be a presentation, and next Tuesday I will offer the optimization algorithm and we will play a game. Each of us will pretend that we are little computers that follow the optimization algorithm. I hope you will enjoy it. Whew. So potential due to this contribution from quantum, from electronic part, the potential energy surfaces for each electronic state are slightly different. Here is just a little just a second. Okay. So here is just a little movie from Lab 2 in other year. You all did similar thing and you can do it better than I. So upon humans create a model, there should be optimization algorithm that finds the positions of ions where interatomic forces are minimal, not minimal, optimal, where the forces are minimal and and energy is minimal, and everything we do serves the goal to discuss the algorithm, how this optimization happens. So through this optimization algorithm, some bonds become shorter, some become longer, and the energy minimizes. So how I can interpret the movie from the last time? Suppose, again, we are doing a lot of hypothetical considerations. It is not yet an actual computation, but suppose I do have a method that immediately solves electronic Schrodinger equation for each position, each atomic position. Then my plan for optimizing geometry will be as follows. So for provided set of ionic positions, I need to quickly solve Schrödinger equation for all electrons and find eigenvalue for either ground state or excited state if you look at excited state optimization. This eigenstate makes contribution to potential energy surface. Then I compute gradient and apply equation of motion for ions to update interatomic positions. After interatomic positions are changed, I take these ionic positions and solve electronic equation once again. And then this procedure is repeated again and again. Some of you, or maybe all of you, who already practiced geometry optimization in Avogadro recently, or practiced molecular mechanics in your career, molecular dynamics, may say, where is this part of electronic structure? I do 1 million atoms in 1 minute. Something is not explained correctly here. And those of you who give this statement are correct. So in practical computation, there is a very large class of problems where bonds between atoms do not break. So if bonds do not break, if temperature is low enough, if we do not care about conductivity, optical absorption, chemical reactions, one can neglect solving this electronic equation. Instead, one uses so-called force field parameterization, where we hire other scientists who solve this electronic equation for given pair of atoms at certain interatomic distances, and tabulates forces, tabulates these eigenstates, and saves them into the software for quick and efficient optimization by molecular mechanics and force field solvers. So this is possible, and I'm not going to lie you and skip this part. But if you want to be general, if you want to deal with situations when molecules adsorb on a surface, when bonds are broken, where there are chemical reactions, combustion, when we need conductivity, photovoltaics, optical absorption, then electronic equation cannot be neglected. Therefore, be included into consideration. So some people can do successful research career without solving this equation at all. But it is included in the class because even if we skip this equation, we use results of this equation being solved by someone else for us. Does it make sense? Okay. So here there will be slides with a lot of boring stuff. If you fall asleep, I do not mind. And I already introduced most important concept and most important summary of today's meeting. The rest are truly boring details. So if you take physics, you know this name, right? So for most potential energy surfaces, near equilibrium can be considered as harmonic potential, as parabolas. Eigenstates of parabolas are this Hermitian times Gaussian, like a camel with several humps, right? But another solution for time-dependent solution for parabolic potential is so-called Gaussian wave pattern. When be more sharp this drawing. When the energy is bigger than ground, there is a Gaussian distribution, and there are some oscillations. Oscillations correspond to non-zero momentum, and center of distribution corresponds to the velocity. So in case the width of this Gaussian is small enough, one can assume that it is something like a delta function, and one can use the concept of expectation value. So one can tell that it is either Gaussian or delta function in the vicinity of the expectation value of the ionic wave function. So this is possible, this is important, this is doable if the width of the wave packet is substantially smaller than interatomic distances. And for most heavy atoms, it is true. It is violated only for small ions like protons. Okay. So if you do have curiosity about how this transition from quantum limit to classical limit has been performed, I'll show a couple of equations. But again, it will be not a part of any exam. It will be not part of any assignment. So it's only for your curiosity. If you don't care and do not worry, it's fine. So suppose we know nuclear wave function with and without conjugation. Suppose we need to deal with expectation value of any operator, and we will look on the position operator, but generally one can look on expectation value of any arbitrary operator. Then time derivative, the time evolution of expectation value, can be taken as derivative of each of these three functions: wave function, operator, wave function. Derivative, derivative, and derivative of the operator. So if one replaces the bra and cat, rows and columns, time derivatives according to definition of the time-dependent Schrödinger equation here, then one will reconstruct this equation into this form, So time derivative of observable equals to commutation of this observable with commutator. So it's haha equation. Or if you do not like the word haha, it is Heisenberg equation of motion. So for our purpose, we set up that operator A is replaced by position, and later on we may use commutation relations between position and momentum. So if we practice the haha equation for expectation value of position, it will be commutation between Hamiltonian, nuclear Hamiltonian, and position operator. So the Hamiltonian includes kinetic and potential energy, and commutation means swapping the order of operator and the observable. So in this expression, when the potential energy is a simple function, it is a diagonal function. It consists only on powers of the position operator. Therefore, swapping of the order doesn't matter, and we can cancel. And for kinetic energy, the cancellation is not possible because it includes derivative or includes this momentum. So if one practices it, it will be PPR and then RPP. I do not have a speech defect. I'm just solving quantum equations. And if one carefully practices this PPR minus RPP, one may use the commutation relation between position and momentum, plug it in 2 times, and after doing this machinery, one will be able to reorder operators in the same order, PPR, PPR. But as a price for its reordering, one will get an additional term. So these reordered terms are cancelled, and the term originates from commutation, and it will explicitly include the momentum. So out of this consideration, we are getting the time derivative of the position equals expectation value of position equals to expectation value of the momentum with constants, like imaginary unit, Planck constant, which cancels. And after canceling all elements, we will get the expectation value of the position equals expectation value of the momentum over the mass. So if we remove these angular brackets, it will be like a natural equation from like first high school lecture on mechanics. Velocity equals momentum divided by mass, right? But here, instead of velocity and momentum, we are telling smart words about expectation values of the nuclear wave function. So we got it from equation of motion for position from Kaha equation, and one can also obtain the same style equation for if one replaces the operator A with momentum operator. So momentum is derivative over position. One needs to find the commutator with only potential energy, because operator and its power can use this P squared predominantly commute. So if one practices this little exercise, then it will be just derivative of product function, and through this practice, one will get that the change in time of the momentum equals to the expectation value of the gradient of the potential surface of the potential. So the only difference from our classical vision is that derivative is not outside of this bra and cat notation, but inside. And this derivative submerged inside the bra and cat is referred to as Hellman and Feynman forces. So if we bring together the equation for momentum and equation for position, this one, and for position for momentum, we will see that we can make as an additional approximation, we can put derivative outside of these brackets, and then we will see a coupled system of equations. One equation shows how position is changing, but it depends on momentum, and another shows how momentum is changing, but it depends on the potential, which in its turn depends on the position, on the expectation value of the position. So This result of transferring from nuclear wave function to this equation of motion for expectation value can be referred as Ehrenfest theorem. So it is not our frivolous return to Newtonian mechanics, but it is all justified. And one can plug in one equation into another. If one takes another derivative of the first equation, then here instead of momentum we will have also time derivative, and then we can replace this time derivative over the content of this equation. So we will obtain second derivative d dt squared over r equals minus 1 over mass ddr u of r, which reproduces the Newtonian equation of motion, right? So second derivative is acceleration, minus gradient over potential is force, and here we have a mass as an inertia, proportionality between force and acceleration. So if we admit this stuff, then we are arriving to the second box. So we consider this Hamiltonian equations, and they bring us back to the Newtonian equation of motion. So I will happily answer questions and discuss further, but if you are not objecting about these steps, then from now on, at least for one lecture, we can focus on solving not Newton equations of motion. We can solve for optimization problem. We can formulate an algorithm that will find such interatomic positions for multi-ion system, for a molecule of any size, that will find minimum of energy, minimum of forces, which will mean most probable conformation of a molecule, most stable conformation of a molecule. So basically, we should be done. Yes, we should be done. And on the next lecture, in a week from now, I will introduce flowchart diagrams and set up an algorithm that first we will practice as humans, and then we will consider how computer solves the algorithms. Whew. I'm done. So, and we are ahead of time. The plan was to do everything in 1 hour, but we are done in like 48 minutes.
For the first time, you finish it early.
Okay. So, anyone, let me probably stop sharing and come back to more visual. So, any questions are encouraged. If you do not have questions, you may disconnect from the meeting, and I'll plan to be in the QBB 132 tomorrow for the lab number 3.
Excuse me, Professor, for the potential energy surface homework, should we prepare some explanation and picture and send it to you, or no?
Yes. Please do not spend much time. Do maybe 1 or 2 sentences, 1 figure, and maybe 1 equation. My hope, it's not a secret. Probably I will probably I will teach this class again in the next year, and maybe the best slide from the class will be used with a credit to you guys, will be used in the next year lecture, and I will announce the champion, because I'm trying to draw it from year to year, and I need to admit that my drawings are ugly, and I'm not as creative to find a good picture from online. Maybe you'll do it better.
So, because I was thinking we were gonna like share them today over the Zoom and talk about them, so I just created a slide. Would that be okay to just send the slide to you?
Yes, yes. And you'll have plenty of time to share and present. So first time on Friday about the basic skills, and I'll focus on, well, we'll do everything that we did before on tomorrow, so that everyone will get equipped. And if you connected a little later, in the first 5-10 minutes of the meeting, I was given the context about the Avogadro transferring files and converting to Gaussian input file. So whoever presents on these subjects may remind it. So even if more than one person reminds about importance of transferring files and converting to Gaussian input format, it will be appreciated. Whew.
One other quick question.
Please.
So I think it was on last Friday, we all like wrote our names on a bunch of those different topics. Were we going to present on all the ones we put our names on, or we're going to just pick one and present on that one?
I'm behind my schedule. My plan was to summarize your choices and send you a final schedule. Basically, we will present what you selected for. But if you selected something at the beginning and at the end, I will reorder so and create, so to say, a schedule of presentation, a program, like in a program of a conference. And,
Sounds good.
My plan was to do it before today's lecture, but I apologize. It was like a sequence of back-to-back meetings with no time to breathe.
Oh, good.
Okay. I wanted to briefly chat with Boston. And it is not a secret for anyone, but it will be about his project. So if there are some questions about the class in general, feel free to ask first. No, I'll ask my question to Boston, but feel free to stay and discuss, and maybe more discussions will come in. So, Boston, originally you wanted to do this 4 compounds, like I don't remember, but I have it in my records. And later you told that you are interested in perovskite photovoltaics. Is it something that you want to do only for the course, or it is strategic navigation of your group leader?
It was a combination of the fact that I liked this stuff because I was reading a lot on this before the class started, and I really liked doing all the computational chemistry stuff. And what I was doing beforehand, last semester, I wasn't enjoying that much. So I thought switching to more computational stuff would be better for just me. And so that's why I made that switch. It wasn't because of the class, or not because it was be applicable to the class. It was because I think that was just the right direction for me to go. And before I had even thought about it, Dr. Zhang had mentioned that to me before. I was like, hey, there's this also thing you could do where instead of working on the CZTS stuff, we could work on modeling of the perovskite materials, specifically halide perovskites is what I'm going to start off with. And so, yeah, I've been working on that for a while now. I've been doing some stuff with CCAS and trying to work with VAST and get some simulations going on that.
Cool, that's cool. Do you have plans, or does your advisor have plans to do experiment on halide perovskites?
That's one of the things that we were kind of talking about. So right now, as far as I'm aware, there aren't any plans to do actual experiments. So the way I would compare any results that I got from my simulations would be to look at papers that other experimenters have done, whether their own simulations or actual experimental results. But I was also talking to one of the other students in my group who's working on similar research. He's not working with perovskites. He's working with another compound that I'm forgetting the name of it right now, but he said that it might be really interesting if I can get going and do some of my perovskite stuff, if I can also model his compound in applications for solar energy technology. So, and if I were to do that, then I could obviously compare my simulations to his current work. So that might be interesting too, if I can get that done.
Okay. So my thought was that it will be not efficient if you scatter your efforts and do one thing for a project, another thing for physics. If you combine all your efforts together, it will be much more efficient. And if you and Dr. P can have interest in perovskite solar cells, in the past I used to do experiments, and I have some like chemicals precursors which you may need for thin film deposition. It's the same as possible experiment. So I'll share it if it is among your plans.
That'd be awesome. That would be really cool if we can get that going, because yeah, you know, to compare them to actual results would be much better than just going off of the simulations.
Okay. Okay. Yes. Thank you, Boston. I think this question is resolved. I was looking quickly at what keyword that Kea told to me. So it looks like the polymers you are looking at is the material. Is it material for three-dimensional printers?
No, it's not a three-dimensional printer.
Or is it something that restores shape after heating?
Yeah, it's
Okay.
like we know that there is two kinds of polymer: thermoset, thermoplastic. Then this one is like a heat treamer. It has both components. Like sometimes it behaves like a thermoplast and thermoset. So that's why people are want to working on that.
Okay. Okay. So we are yet quite far from the project which we go on during the last month. But you may, while you are reading papers on it, you do see chemical structures of polymers, right?
Yeah.
Repeating unit. So you may start trying drawing them by Avogadro Gauss view and optimizing, and just maybe you will create them differently for the project, but if you get hands-on experience, it could be helpful. Or if you find online data for the structures, just think about it so that
Okay.
prepare ahead.
Mhm. But for for the upcoming presentation, I don't need to do that.
No. It is for the end of semester. Just in previous years, everyone was very interested and enthusiastic about projects, but it's always many other activities. And when there were evaluation of the course and instructor, I constantly get the same criticism, like, why don't you start projects earlier? So I'm just giving hands on. For Sarah, I think you do have samples of computational samples of the clays. Do you?
Oh, you mean the model for this class?
So you mentioned that you are interested to do clays, right?
Yes, yes.
So are you already working with them?
Yes, for the molecular modeling, yeah, molecular using molecular dynamics, yeah, I'm currently working on the clays.
Do you use periodic boundary conditions?
Yes.
Okay. So for the class later on, we will need a model with the smaller the better. The smallest possible periodic model. I know that your force field technique can take million atoms. The software that we will be using in class will take maybe up to 300 atoms. If you go beyond, it will slow down drastically. So one can select just very small unit cell and start depositing smaller monomers and then compare versus analogous results of force field.
Yeah. Is there any websites to find some models for clay regarding the, I don't know, VASP? We are going to use VASP in this class.
Mm-hmm. I will show how to convert XYZ model into VASP input. It will be one of the main skills in the like third month of the class.
Okay. Thank you.
And for Lina, I probably least prepared for your project. You need to prepare models, or at least share with me where to take them. If you would be interested in metal organic frameworks, I would be much more helpful. But for bigger biological molecules, I need to learn from you more.
Yeah, I know for biomolecules, it's maybe kind of different and needs to be really accurate about the model that are. Yeah, so I'm planning to do like research on that and prepare a design or more information about it, and I'll be like maybe we can discuss and like getting like a better idea about what's the good plan for that. So kind of, yeah, I'm interested in doing simulations to be able to predict maybe binding force. It's not easy to get binding force measurements experimentally, and if we can get a reference as a computational work for that, it would be great for us. Just comparing our data with these results. So yeah, I'm planning soon to do like more to do some work on that, getting better idea earlier than I want to wait for the end of the semester, but just yeah.
Okay. Then I obtained answers to all my questions. I don't have any more tonight. So I'll stay here just in case you come up with more questions. But truly, we are completely done for today's program. And I'll wait, and if there will be no questions, I will just.
Yeah. Good night, all. Good night, Dr. Helen. Bye.
Have a good night.
Good night.
Goodbye, all.
Goodbye.
Professor, so for the next presentation, since next Friday we have a presentation, so I just need to make a PPT.
Yes.
I need to take a screenshot. First, I need to make a model, then a screenshot, and then I need to explain this.
Right. Exactly. And it shouldn't be long. It should be like maybe 4 slides and 5 minutes presentation.
Yeah, I can understand. It's so easy. You can say that you can make a video for that. Then that will be easy for us because we can then show the how to build a model. Then um,
Yeah,
yeah,
you can.
video.
By the way, you can just take a video with a cell phone and then attach it to the PowerPoint.
Okay, yeah, I will try, but I don't know I have much time or not because today I work from 5 a.m. to 3:20 p.m. 5 a.m. to 3:20 p.m. So
It's a
long.
lot. It's hard. I can understand.
Yeah. Then after that, I just it's not a sleep, just freshen up myself. Then after that, just class. Then again, I will start to make that PPT now.
Excellent, excellent.
Okay. So I already read few paper on Vitrimal.
Mhm.
Yeah, but the thing is, I can understand the some physical meaning of that, the graphical explanation I can understand, but the thing there are so many chemistry parts. Yes, those things hard for me because uh, I'm from my background is civil engineer, so uh, I forgot chemistry totally. Few things I understand like covalent bond, then Hamiltonian. You explain those things. Then few things I can understand and I can catch those things easily. But the equation, then they're like they first they create a bond, then after that when if you apply heat, then they started to reshaping. Means first they create bond, then they break bond, they break a bond, and then again they create a bond. So those things it's difficult to understand. Still now I'm not able to understand those things.
That's fine, but when you read papers on the
Yes.
subject, you can share them with me, so I also glance through and maybe
Okay.
I will be able to to help to answer your questions more specifically.
Okay. Okay. Then I will. Um, Okay. Thank you, Professor.
Okay.
Actually, I love your lecture out totally. Means in your lecture you explain so well.
Ah, thank you for your good words.
Okay. Good night, Professor.
Okay, good night.